So now do the calculation of the energy balance for a planetary body that has an atmosphere. So this is the ground, the surface. And let's imagine that I have an atmosphere. I'll drop the atmosphere here. Okay, so this is the atmosphere. Okay, and this is the surface. And we have sunlight coming in at 100 units. Okay, so the 100 units comes in. All right, and the atmosphere is transparent to visible light, and solar energy is primarily invisible. 30% gets reflected completely, and reflected really just means bounced off, so it's the same kind of light. So in some ways, part of it might bounce off of clouds in the atmosphere. Some of it may make it down to the ground and get bounced off by ice or ocean or something like that. And the total there is, let's say, 30 units. Okay, which means, of course, that 70 units gets absorbed in the surface. The surface then warms up, and we'll be interested in the temperature of the surface. I'll call it TS. And it then starts releasing energy up. So this is energy out from the surface, so I'll just call it ES. And the interesting thing is that the energy that's released from a planet is generally in the infrared. The atmosphere is primarily opaque to infrared, so most of the energy that is released by the planet actually gets absorbed in the atmosphere. What does that do? That increases the temperature of the atmosphere. So we have temperature of the atmosphere now, which then itself emits energy. So again, also in the infrared. This time it emits energy both up and down back toward the surface. So we have energy that the atmosphere is releasing going up and down. And notice what's happening is that now the sun, they have the solar energy here, the surface is receiving energy from the sun, and it's receiving extra energy from the atmosphere. And all these energies will adjust, all the temperature for the surface and the atmosphere will adjust themselves until everything is in balance. So we need to look at the balance equations for this. So let's look at those. So in each case, we pretty much look at in and out. Okay, so the beginning we'll look at the surface. So at the surface, we have incoming is 70 plus the energy from the atmosphere, EA. That's equal to the energy from the surface. That's the only thing that's going out. It's the only out arrow. At the atmosphere level, what we have is coming in, we have ES, and going out, we have EA up and EA down, so we have 2 EA. From space, we have 100 coming down. If you there's no in or out, for space. So if we let's say down is in right now and up is out. What we'd have is we'd have 100 in and 30 plus EA going out. Notice these have 3 equations with 2 unknowns, so it's over specified, but we'll actually see that anyway. So what values of ES and EA would balance in these in this case? Well, if I were to take this ES, kind of 2 EA here, and plug it into there, then what I get is I get 70 plus EA is equal to 2 EA, or 70 is equal to EA, which also means if twice that is ES, that means 140 is equal to ES. So we have here, this is equal to 70, this is also equal to 70, this ES is equal to 140. Notice we get the Earth's surface is getting 70 from the atmosphere, 70 from the sun, and to balance it has to emit 140. In order to determine the temperature, we use the relationship that we used before, namely that E is equal to temperature over 88.5 Kelvin. This is the round unit method to the fourth. So what I get is 140 to the 0.25 times 88.5 Kelvin. And this is 304 Kelvin. For the atmosphere, I do the same thing. 70 to the 0.25 times 88.5 Kelvin, and that's equal to 256 Kelvin. Those are the two temperatures that we get. There are a few things that we need to note. First of all, the temperature of the atmosphere is exactly the same temperature that we figured out for a planet without an atmosphere at all. The temperature for the surface is warmer than it would have been had the atmosphere not been there. So by putting an atmosphere here and having the interaction with the infrared radiation and the re-radiation going back to the surface, we actually warm the surface, and this is what is called the greenhouse effect, even though greenhouses don't really work that way. It's also true that the balance is true for every single point. So for out in space and the atmosphere and the surface. Any change, so if I were to increase the surface temperature artificially for some reason, everything would then readjust and go back to the balance. Now, some of the major assumptions here, the biggest one is that the atmosphere is not entirely opaque to infrared. So a little bit leaks out, and we can do the calculation with that with that leak just to see what would actually happen. But we can add whatever complexities we want to this model, to these calculations, and understand where the system will readjust.